Welcome everyone. My name is Cassimon, and I'll be presenting our survey on discrete multi-objective reinforcement learning benchmarks. Many problems are inherently multi-objective problems. A multi-objective problem is a problem that consists of two or more objectives that can't be optimized concurrently. As an example, think of a corporation trying to maximize its profits while also minimizing its environmental impact. In order to deal with these problems, many multi-objective reinforcement learning techniques have been devised over the last several years. In this paper, we wanted to investigate how these multi-objective reinforcement learning methodologies are being evaluated. More specifically, we wanted to take a look at the benchmarks that are being used and what properties they have. But in this paper, we will only consider fully discrete benchmarks. This means benchmarks with a discrete state space and a discrete action space. And the benchmarks we consider can be both deterministic and stochastic in nature. In the field of multi-objective reinforcement learning benchmarking, an important paper is Empirical Evaluation Methods for Multi-Objective Reinforcement Learning Algorithms, published by Vaplu et al. in 2011. In their paper, they note a lack of a rigorous standardized benchmark suite for multi-objective reinforcement learning approaches. In their paper, Vaplu et al. Highlighted multiple problems in multi-objective reinforcement learning literature. The first of these problems is that methodologies were only being evaluated on a small selection of benchmarks. These selections might not include certain challenges, such as partial observability or stochasticity. Another issue they found was that there was very little overlap between the benchmarks that were being used in different publications. This made a comparison between different methodologies difficult or even impossible. Finally, they also observed that some of the benchmarks being used didn't have a known Pareto fund. This makes assessing the accuracy and the performance of these methodologies difficult, since there is no reference point to compare to. Based on these observations, Vaplu et al. Proposed a benchmark suite consisting of four benchmarks. This benchmark suite includes the deep sea treasure benchmark, a multi-objective version of the puddle world problem, a multi-objective version of the mountain car problem, and finally, the resource gathering problem. In our paper, we analyzed a number of multi-objective reinforcement learning publications to find the benchmarks that they are using. We then evaluated these benchmarks on four criteria: whether or not the Pareto front is known, how complex the benchmark is, how widely adopted the benchmark is, and how easily available it is. Finally, based on our observations, we proposed an extension to the existing deep sea treasure benchmark. Let's take a look at the criteria we used to evaluate these benchmarks. As we mentioned already, knowledge of the Pareto front is important to accurately assess the performance of a methodology. Next, we use the size of the state action space as a proxy for benchmark complexity. Usually, benchmarks with a larger state action space are more complex. We also assess the adoption of each benchmark. This helps us to evaluate the lack of overlap between publications that Vaplu et al. Pointed out. Finally, we assess the availability of each benchmark. Since it is usually not possible to completely define a benchmark within the confines of a paper, having access to an implementation of a benchmark is important in ensuring reproducibility and allowing other researchers to build on your work. Using search engines like Google Scholar and search terms like multi-objective reinforcement learning, we were able to find 14 publications that evaluated their methodology using fully discrete benchmarks. We ignored benchmarks that required a significant amount of domain knowledge, since this can present some difficulties in using and interpreting the results of the benchmark. Finally, from these 14 publications, we selected 11 benchmarks to analyze further. The first criterion we evaluated these benchmarks on was knowledge of the Pareto front. Except for one, the Pareto front is known for every benchmark in our dataset. The only benchmark with an unknown Pareto front is the multi-objective Super Mario Bros. As we mentioned earlier, it is important that this Pareto front is known so researchers can accurately assess the merits and demerits of their methodologies. The next criterion we evaluated was complexity. On this graph, we can see a histogram showing how often benchmarks with a certain size of state action space were used in publications. Using this data, we calculated the weighted mean and weighted median of the state action space size. Weighted measurements were made based on how many publications used each benchmark. In this graph, the weighted median in red has a value of 254, and the weighted mean in orange has a value of 29 million. We note that the mean was likely influenced by outliers. When we look at the data in tabular form, sorted by decreasing complexity, we see that the outlier on our histogram was multi-objective Super Mario Bros. Among all the benchmarks, we notice that the state action space of most is very small, with only 3 benchmarks having more than 10,000 state action pairs. This is also an issue that was pointed out by Van Ploeg et al. In their 2011 paper, where they noted that good MORL benchmarks should be complex enough to warrant the use of function approximation algorithms. We can also compare this list of multi-objective reinforcement learning benchmarks to single-objective reinforcement learning benchmarks. For this comparison, we selected Space Invaders v0 and Space Invaders RAM v0. We see that when comparing our multi-objective reinforcement learning benchmarks to 2 single-objective reinforcement learning benchmarks, that the single-objective reinforcement learning benchmarks end up towards the top of our list in terms of complexity. After analyzing our benchmarks in terms of complexity, we will now compare them in terms of adoption. In this table, each row contains a single benchmark, and each column contains a single publication we analyzed. We can see that for many of these benchmarks, they have been used in 1 or 2 publications, indicating that the lack of overlap that was highlighted by Van Ploeg et al. In 2011 is still present. When aggregating the statistics, we do see that there has been some convergence. The deep sea treasure problem has been used by 8 different publications, with this number going up to 9 if we also include the variations of the deep sea treasure problem, namely the image-based deep sea treasure and the pressurized bountiful sea treasure problem. Finally, we compare our benchmarks based on their availability. We see that almost every benchmark has at least one open source implementation available. We also notice that around half of the benchmarks have Python implementations. We specifically note Python implementations because the majority of machine learning research today is being done using Python, making Python implementations significantly easier for researchers to use. Finally, we also like to note that even though DEED has no published implementations, all of the necessary equations and data have been published, still making it viable for researchers to evaluate their methodologies on DEED if necessary. Based on the observations we made before, we would now like to propose an extension to the existing deep sea treasure benchmark. We would like our benchmark to have the following features: a large action space that is achieved without the use of image-based observations. We would like our benchmark to have at least 3 objectives, and we would like a deterministic transition model. Besides these features, we think it is also important that we keep similarity with the existing deep sea treasure benchmark to aid in adoption, and to make sure that we build our deep sea treasure extension using GIM so that it's compatible with all major reinforcement learning frameworks. Based on these features, we came up with this benchmark. Similar to the original deep sea treasure problem, the submarine is tasked with finding treasure. The submarine's observation consists of the submarine's velocity and the relative coordinates of all treasures. The submarine can move around by accelerating in the x and y direction. Finally, the submarine is tasked with optimizing 3 objectives: the treasure and time objective, similar to the original problem, and the fuel objective, which is determined based on the submarine's current acceleration. Our benchmark can also be configured in different ways. In this paper, we considered 2 sets of treasures: configuration A, which uses the same treasures as the original deep sea treasure problem, and configuration B, which consists of 58 treasures. Note that in order to compute the size of the state action space, we assume that the depth of each treasure increases linearly after the first 10, and that the treasure values are adjusted accordingly. This allows us to compute the size of the state action space without knowing the exact Pareto front. If we evaluate our proposed deep sea treasure extension using the same evaluation criteria we used for the other benchmarks, we see that our configuration A ends up 3rd in terms of complexity, with our configuration B becoming 1st. We note that the Pareto front for configuration A is known, while the Pareto front for configuration B is not known. In terms of the size of the state action space, configuration A contains 36,000 state action pairs, while configuration B contains 339 million. Of course, this benchmark being new, there is no adoption yet. Finally, in terms of availability, the source code of our benchmark is available through GitHub. Well, we also published a pip package so that researchers can easily pip install DeepC Treasure to get started with our benchmark. Finally, based on our earlier observations, we can draw some conclusions. First, in terms of Pareto front knowledge, the current state of benchmarking is good. Almost every benchmark has a known Pareto front. Unfortunately, it is not possible to determine the exact Pareto front for all benchmarks. If this is the case, the Pareto front attained by a specific methodology should be published as numerical data, so that other researchers can accurately compare the Pareto fronts they found using those of other methodologies. We notice that there is a lot of variation in terms of complexity. Low complexity benchmarks are very useful for proof of concept research, while high complexity benchmarks are important for proving the scalability of methodologies. We note that the adoption of high complexity benchmarks is still limited compared to that of low complexity benchmarks. When evaluating adoption, we note that there is still room for improvement. Evaluation using the DeepC Treasure benchmark is a good starting point, but ideally, authors should also consider more complex benchmarks like the one we proposed, or multi-objective Super Mario Brothers. Finally, almost every benchmark has an open source implementation available. Unfortunately, not every benchmark has a Python implementation, but using existing implementations in other languages, writing a Python implementation shouldn't be overly difficult. Next, I will conclude this presentation with some possible notes for improvement. First, in this paper, we measured the complexity of different benchmarks using the size of their state action space. Fortunately, this measure of complexity is far from perfect, since it omits any complexities in the transition function and it is not usable in continuous domains. Next, in this paper, we considered 4 evaluation criteria: whether or not the Pareto front is known, complexity of the benchmark, how widely it is adopted, and how easily available it is. Besides these criteria, there are many more that could also be interesting to research, including stochasticity and whether or not the benchmark is fully, jointly, or partially observable. Finally, we believe an update of the benchmark suite composed by Van Ploeg et al. Is in order to include some of the more complex benchmarks that we looked at, such as the Super Mario Brothers or the benchmark that we propose. On that note, I will conclude my presentation. Thank you all for your attention.